Am I audible without mic? Today I am going to talk about this indefinite causal order enables perfect quantum communication with zero capacity channels. So maybe you have already heard of quantum switch, which is a higher order map, also called a super map, which takes as input some quantum channel and output some other quantum channel. So a natural question in such a scenario is that if the channels are noisy, so if you put some noisy input channel and you can get some other channel which has less noise, then it will be useful for a communication scenario. So we tried to look into that. We focus mainly on the communication advantage of such higher order maps. So this is based on one of our works. So this is based on one of our recent work, and to better motivate our work, let us begin from the beginning. And it all started with the seminal work of Shannon, which is in this work, a mathematical theory of communication, where there is this information source, and then the information is encrypted into some physical system and sent to the receiver. But in the intermediate region, it can go through some noise. And on the receiver side, this is again deciphered, the message is deciphered. So in this model of communication, this is a pretty straightforward model of communication, and in this setting, there are two assumptions. The first one is that the carriers of information and the communication channels are classical systems, as you have seen examples of these in today's morning talk by Professor Liu. And another implicit assumption is that this information travels along predefined trajectories. Like starting from here, there is a past, there is a future, and in the intermediate time, it travels in a well-defined trajectory. Okay, so but we all know that physical systems at the fundamental level are not classical, so they obey the laws of quantum mechanics. And it was also known to Shannon. I mean, in times of Shannon, it was already known that systems are behaved in a quantum way. But what was not known is that these quantum systems can give rise to certain counterintuitive tasks, such as QKD. So came the quantum Shannon theory, where the carriers of information became quantum particles whose internal state can be in a superposition of the basic classical states. But the other assumption that the information travels along predefined trajectories, it remained the same. So it did not change. So now we ask this question that, can we move beyond this notion of predefined ordering? Okay, for a communication system, there is a sender, there is a receiver, but in the intermediate region, it may not follow some predefined path. So which is very much in a sense quantum. Okay, and also if we can successfully make such a setting, then does it find any application in quantum communication? This question that I input some noisy channel and as an output I get some channel with less noise. So here I state our main result, which says that noisy communication channels unable to reliably transfer quantum information can be made useful for noiseless communication. So this is the maximum you can ask for, that there are input channels which are maximally noisy, like it will erase all the quantum information, but then as an output you will get a channel which is completely noiseless, like identity. So this is accomplished by switch. I will go into the detail of that. Okay, so but before I describe it, let us just revise this problem of quantum communication. So we are trying to transfer unknown quantum states reliably to some distant location by using available communication devices. So this is important. So you are given certain available devices and you want to make use of that, you want to combine them in such a way the transfer rate is maximum. Okay, and as you all know that this quantum channel is given by CP2P maps, and the action of this quantum channel is represented by these Strauss operators which satisfy certain conditions. Okay, and the relevant quantity for quantum communication is the coherent information. You have already heard about it. And finally, the quantum capacity is given by a regularization of this coherent information. Okay, so now our task reduces to an efficient composition of available channels so as to maximize the rate of this information transfer. So let us begin with the simplest scenario where I have given two noisy channels. So in how many ways I can combine them? So one obvious way is that they are ordered in the usual Shannon sense, like with a predefined trajectory. That is first E and then F, or first F and then E. We call it order. But quantum mechanics is compatible with more exotic types of combinations, like such as these. Okay, so what is this? Here, there is this target system which carries the information. Now it can pass either through E or through F. So there is a control system which can decide whether it takes the red path or the blue path. And again, this control system is a quantum system, so it can be in a superposition of both of these two states. So you can actually have a superposition in path of these channels. And again, the other kind of combination could be like this. Either the target system first passes through E and then through F, that is the red line, or first through F and then through E. So this we call the superposition in order of the channels. I will be mostly talking about this, but again, to compare the advantage of this thing with respect to this thing, I will just briefly describe this thing also, but later. Okay, so now let us discuss this superposition in causal order, which is the quantum switch. It was first proposed by Giulio in 2009, and then it was experimentally simulated by many experimental groups. Okay, so now how does it work? Okay, so let us say you are given as input two quantum channels, E and F, with these Strauss operators. Then the Strauss operator of the output channel is given by this, where this one, for this, one can try to understand this Strauss operator in such a way that for this term, E acts first and then F, which is for the control state 0. And in this scenario, F acts first and then E for the control state 1. So finally, the output channel acting on the target system is given by this, where this omega is actually the state of the control. Okay. So in a communication scenario, what happens is that finally the control system is with the receiver, and the receiver performs some measurement on the control system and obtains some conditional channel on the target system. So now what we want is that we will input these channels as noisy, but as conditional channels, whatever is obtained by performing a measurement on the control system, finally by the receiver, we want these things to be noiseless. Okay. But there exist some other applications of quantum switch in channel discrimination, computation, communication complexity. I just mentioned them just for reference. Okay, so now let us come back to our task of communication assisted by quantum switch. And let us say we start by sending classical information. We ask this question that whether one can reliably send classical information when the interactions are maximally noisy. So the input channels are maximally noisy. It erases all the classical information. For example, one can take completely depolarizing channels. Now one can see that if I have definite order among the channels, like first E and then F, or first F and then E, then it is impossible to send any classical information. But using quantum switch, it is possible And this was shown by Daniel, Sinha and Julio in this work, where they called it causal activation of classical capacity. Okay, but we will be looking at sending quantum information. Okay, so similarly, we can look into the scenario of maximally noisy interaction, which erases all the classical information. For such an example is completely repolarizing channel. But what we find is that with definite order it is impossible. Everyone knows that. But even with quantum switch, it is impossible. So this is our first result, which we show in this work, that using quantum switch, one cannot activate classical capacity in an extreme sense, like from 0 to 1, 0 to non-zero, sorry. Okay, so we give it by this, we ask this precise question, that is it possible to activate the quantum capacity of channels with 0 classical capacity? So initially the input channels are of 0 classical capacity, and then we want the output channel to have some finite quantum capacity. It is not possible. So we give this by this theorem, that which shows that for every pair of complete erasure channels and for every state of the control, the switch channel is always entanglement breaking. So it will always have quantum capacity 0. So what does it show? It shows that there is a fundamental limit to which, how far you can push this quantum switch to activate capacities. And also it says that every channel that exhibits activation of classical capacity from 0 to non-zero does not exhibit activation of quantum capacity. So there is some limit. Okay, so now let us make our life a little bit simpler. We don't consider maximally noisy interactions, but such interactions which erases all the quantum information. So example of such are the entanglement breaking channels, which has quantum capacity 0, but the classical capacity may not be 0. And what one can see that even using them in definite order, it is impossible to send quantum information reliably. But we show that by using quantum switch, it is possible to send quantum information through these entanglement breaking channels reliably. And not only that, you can do this in a best possible way. So this is the perfect activation of quantum capacity. And this is another result. So to demonstrate that, let us take the example of Pauli channels. So let us say I am inputting Pauli channels, which are random unitaries acting on the target system. These are the Pauli unitaries. And so the Krauss operator corresponding to the switch will look like this, where these sigma I, sigma j are the Pauli operators corresponding to the two channels, the Krauss operators. And the switch channel looks like this. So these are the conditional channels that I obtained by performing a measurement on the control system. So this is a combination of, this is again some kind of depolarizing channel, and here you have only the XYZ channel. Now observe here is that if you make P0 to be 0, then this whole thing vanishes, and this C plus turns out to be an identity channel. And out of this P1, P2, P3, if you make any one of them to be 0, then this C minus reduces to some rotation, some unitary. If you make P1 to be 0, then this term goes up and this term goes up. So it will remain only the remaining part will only be the X rotation. So this takes us to the Pauli XY channel. So let us say I make P0 and P3 to be 0. So this is a channel which has quantum capacity 0, because this is an entanglement breaking channel. And what one can see is that if I take the initial state of the control system to be the plus plus, it is the equal superposition of 0 and 1. And finally we measure the control system in the plus minus basis, then the conditional system, the conditional channels comes out to be either identity or Z. And it also depends on the outcome of the measurement. So one can see that from the looking at the measurement outcome, one can see whether it is identity or Z. So if it is Z, then you can rotate it and make it perfect. So perfect error correction is possible. So in this way, this output channel turns out to be a completely noiseless channel, and so it has maximum quantum capacity. Okay, so now, okay, so far it is good, but now one can ask that whether this is a unique feature of indefinite causal order, whether one can do this kind of activation task by using superposition of channels, as in the sense of putting them in parallel or using some control system to either go through this or this. Okay, so if we consider the superposition of channels, there can be many possible ways of superposing channels. One is the superposing of independent channels, where the environments are independent. So these are independent paths which are controlled by some control system. And there could be superposition of correlated channels. I will come to this later. But there are some problems considering this kind of situation. So to overcome that, people have proposed certain vacuum extension of these channels. The details can be found in this work. But what is important is that this kind of combining channels is also advantageous for communication scenario. And this is shown by Abbott et al. In this work, this communication through coherent control of quantum channels.
So what does it mean actually by superposition of channels?
Okay, so there is this target. This target will either go through this channel or this channel or this channel. So this is controlled by some control system. And the vacuum extension means that when the system is actually going through this, then these channels are actually acting on the vacuum. So the whole description of this setup is given by the action of the channel on the target and the vacuum. So this is the vacuum extension. Okay, so there is nothing fundamental. So from this thing we learned that there is nothing fundamental about the communication advantage of indefinite causal order. But then we ask this question whether perfect activation is possible by using this kind of independent superposition of independent channels. What we find out is that this is not possible. This is a no-go theorem. That suppose we encode a message in a finite dimensional system and pass it through superposition of finite number of independent channels, and if all of the channels are noisy, then the message cannot be perfectly decoded. So this perfect activation may have some fundamental nature which tells us that only indefinite causal order can enable it. Okay. Yes, so this establishes a fundamental difference between the superposition of independent channels in space and superposition in time, which we can understand in terms of superposition in order. Okay. And as one can expect, this difference comes out because of the correlation that happens in case of indefinite causal order. Right. Now let us come to this superposition of correlated channels. And again, these channels can be correlated in two possible ways. One is the spatially correlated and the other is temporally correlated. The spatially correlated can be thought of in such a way that the environment corresponding to these two channels are spatially entangled. So there is some entangled environment, and then the channels. Then you consider the the vacuum extension of these channels, and then you can get spatially correlated channel. But what we show is that even perfect activation is not possible with these kind of spatially correlated channels. Now we are left with the temporal correlated channel. In this scenario, the environments are not entangled in space, but they are entangled in time. In this sense that the target system or the information carrier passes through two noisy regions. This noisy region actually gives rise to the interaction corresponding to one of the channels, and this noisy region gives rise to the other channel. So the target system first passes through this channel and this channel, or it first passes through this channel and this channel. And as you can expect, if it first passes through this channel and interacts with the environment of this system will remain the same unless it has interacted with the target system. So you need some kind of ideal memory systems to simulate this kind of situations. And what one can see is that the output channel corresponding to this temporally correlated superposition of temporally correlated channels is equal to the output of the quantum switch. So whatever experimental realizations of quantum switch has been done, they have been done in this setup. Like you don't actually have the quantum switch. What you have is actually the temporary superposition of temporally correlated channels, which are correlated over time. Okay. So finally, we'll ask this question: that what kind of qubit channels, not necessarily Pauli, will exhibit this kind of extreme activation? And the answer is very surprising. It is that whatever channel you take and you claim that the quantum capacity is 0 and the switch channel capacity is 1, then you are left with no other choice but this XY channel with some change of basis. So this is in some sense unique. Okay, so to summarize, what we have shown is that the possibility of indefinite causal order gives rise to an extreme activation phenomena in terms of quantum communication. And such extreme form of activation cannot take place in superposition of paths in space, as long as the processes are independent and finite number. And also we show that no quantum channel with 0 classical capacity can gain a non-zero quantum capacity with the existence of quantum switch. So this activation phenomena has some limits. Okay, that's for now, but what next? One can think of application of this quantum switch in case of a quantum network, say not only 2, but there could be any number of channels, and one can think of more exotic combinations passing through this. And whether in those situations this activation phenomena can cover more number of channels. I mean, the set of channels which can be activated by this indefinite causal order can be increased on. It will grow into it. And also the characterization of higher dimensional channels, because here we have only considered the qubit channels, but this characterization for higher dimensional channels could also be used. That's it for now. Thank you.
The way the switch works is that it's a control register which brings the orders, the causal order is up. And the receiver actually receives that register. Is there a scenario in which this can be physically implemented? Like why there will be this control register that will receive that receiver?
Well, because if it is with the sender, then sender can actually encode some message into this control system.
Right.
So this is a kind of cheating strategy.
Yeah, but suppose the sender cannot access this register.
Right.
The question is why, like, is there some scenario that you come up with that will naturally allow the receiver to receive this register? But why would it not just be not accessible to either of the two parties, just some physical process give rise to this superposition? precision versus.
Yes, I mean, the receiver actually does not need to access the control system, but there could be some LOCC between the receiver and the control system. That will be enough, because finally there needs to be a measurement on the control system, and the measurement outcome, which is the classical information, that has to be conveyed from the control to the receiver. That will enable the perfect application.
So you say that the register need not be quantum on the receiver side, but he should be able to demand a certain measurement.
Yes.
And receive the outcome.
Right.
Any reason to motivate
I mean, immediately one can think of it as some interference experiment, where finally you just forget about the path. So this forgetting about the path is some kind of measurement in the Fourier basis on the control system in this scenario. So I cannot just put it into some quantitative term, but qualitatively it looks like this control system remembers which order it has got. So finally, to obtain the interference effect, you need to forget about the which path information. So forgetting this which path information corresponds to performing Fourier basis measurement on the control system. So, I mean, this is the qualitative description. It is not much quantitative.
Thanks. Any other questions before the later discussion? Okay, then let's name some again.